In the previous lesson, we defined the derivative of a function at a particular point, like x equals a, using a limit definition. Just going to recap that one. F prime of a is equal to the limit as x approaches a of f of x minus f of a over x minus a. Remember, this is that alternative slope definition, and this is the slope at that particular point. Okay, provided that this limit exists. If this limit exists, then that means that the left side and the right side have to be approaching the same number. How I interpret that in terms of derivatives, that means the derivative from the left, which looks like this. Look at the new notation here. We have a little subscript, hard to see with red on red, a little subscript with a minus sign. This means, or it's red, the derivative from the left at a is equal to, and now we have a one-sided limit. It's the same thing that we have here, but we're only approaching a from the left-hand side. That needs to be equal to the derivative from the right. Notice that the little subscript on the f here on the derivative has a little plus sign here, just like we would put in the limit. The derivative from the right at a is the limit as x approaches a from the right of that difference quotient. Those two things have to be the same in order for this limit to exist. So this is going to give us a way to show, whenever we wrote down those three possible ways in which a limit can fail to exist, those, where did you go? There you go. Those three things, we'll be able to show why that actually is the case with these examples. So let's take a look here. Example 8, find the derivative from the left and the right for each function below at x equals 0. So we're going to use that alternate limit definition, and we're going to do it from the left side and the right side using those one-sided limits. All right, and there's probably not enough space here. It needs an extra page. All right, and let's go back to this beautiful pastel-ish kind of blue color. So on the first one, we've got f of x equaling absolute value of x. I'm going to find the derivative, so f prime of 0, right, from the left and the right. And see what happens. Okay, so on the left-hand side, this is the way I write it, f prime from the left of 0 is equal to, and then I'm going to take a limit as x approaches 0. So 0, remember in this little definition, that's our a value. That's right there. It's the a value. And now do our little difference quotient here. So I'm just going to write it down first. So f of x minus f of 0 over x minus 0. And then just plug stuff into our function. So when I plug 0 in there, it's 0. That 0 doesn't contribute anything to this one. So when I simplify it, I get absolute value of x. Oh, wait a minute. This should be from the left. This should be from the left. Absolute value of x over x. Does that look familiar? Have we seen this thing before? Okay, so I don't want to stick in a 0. If I do stick in a 0, I do get 0 over 0, of course. So I want to see what this thing is approaching from the left-hand side, which means numbers that are a little bit less than 0. What if I used something like negative 0.1? And then I'd have a negative 0.1 over here. Well, the absolute value on the top is going to chop off that negative sign and make it 0.1, but the bottom is going to keep its negative sign, and 0.1 divided by 0.1 is 1, and I have that little negative there, so it's going to be a negative 1. All right, and then let's do the same exact thing from the right-hand side. So f prime from the right of 0, limit as x approaches 0. Let me see if I can remember it. Plus, there we go. And it's the same exact setup, f of x minus f of 0 over x minus 0. I'm going to have the exact same limit function here, absolute value of x over x. Okay, so now this time, when we're approaching it from the right-hand side, coming in from the right-hand side, it's bigger than, a little bit bigger than 0, so we'll do positive 0.1 and positive 0.1 on the bottom. Absolute value for a positive number does a whole lot of nothing, so I'll have a 0.1 on the top, and then on the bottom it stays 0.1, which gives me a 1. Okay, so now when I compare these two numbers, since they are not the same, then that means that the limit does not exist. Why? Differing left-right behavior. So I am going to write the limit as x approaches 0 of absolute value of x over x dne because of differing left-right behavior. And that is the reason why f prime of 0 does not exist. As a matter of fact, whenever you have a sharp turn, this will always be the case. You have this abrupt change in your slope from a negative to a positive or vice versa. And that is what's happening right here. You can see it right here happening. I've got a positive slope and then negative slope immediately. It's not the same on the left side and the right side of that sharp turn. Therefore, the derivative's not going to exist. Let's take a look at the next one. So on the next one, we have the cube root function. Number 2. So f of x equals cube root of x. And again, we're finding the derivative at 0 from the left and the right. And see what happens. And we'll use this exact same pattern that we have right up here. So the limit, no. F prime from the left of 0 is equal to, now we can put the limit as x approaches 0 from the left. It's the same exact setup, f of x minus f of 0 over x minus 0. What's the cube root of 0? Pretty much 0. So I'm going to have, bring down my limit notation, just the cube root of x over x. If you were to directly substitute in a 0 up in here, of course you're going to have 0 over 0, indeterminate, we got to fix it. How do I fix it in this case? Do I multiply by a conjugate? No, I don't. I just do some algebra. I have like bases, so I can subtract the two exponents. It's an implied 1 down here. So 1/3 minus 1 is a negative 2/3. I'm just going to cram that down to the bottom to keep it positive. So I've got the limit x approaches 0 from the left of 1 over x to the 2/3 power. Okay, so now a direct substitution with a 0 leads to 1 over 0, not indeterminate. Instead, it's a plus or minus infinity. Plus or minus infinity? Which one is it? We'll take a look at what we have. We're squaring the number down here. It's x squared and then taking the cube root, which means that that number is always positive. Let's get rid of this little negative one. Okay, and remember, if you have a limit that is equal to infinity, that means it does not exist due to unbounded behavior. Right? And then, let's do the same thing on the right-hand side. I wonder if it's going to be any different. Oh, don't forget your little plus sign. Derivative from the right is equal to, you know what, I'm going to just jump down here. It's going to be exactly the same as this one. It's going to be this x to the, well, no, you need a limit. Throw that in there. Limit as x goes to 0 this time from the right. X to the 1/3, x to the first would simplify to the same thing that we had before. 1 over x to the 2/3. A direct substitution leads to 1 over 0. And since I am plugging in positive numbers, doesn't really matter. I'm squaring it, so it's going to be positive. This is also going to go to positive infinity, which again does not exist due to unbounded behavior. So putting both of these things together, I am going to conclude that the limit as x approaches 0 from either one of the sides of, maybe x to the 1/3 over x dne due to unbounded behavior. It's unbounded behavior. We interpret that. Remember, we just found a slope there, and the slope is infinitely big. When your slope is infinitely big, we have a vertical tangent line, which again is the reason why back up here we don't have a derivative, right? So on this one, you're going to basically get a slope of infinity. Infinity implies that the limit does not exist due to unbounded behavior, and derivatives, that's all they are. They are limits. All right, and then over here, we have positive slope, we've got negative slope, it changes abruptly, and that means that the limit from the left and the right at that particular point aren't going to be the same.